actually had a question regarding definite integration.
Okay.
And let me just go ahead and pull the question here on the board. So it seems as though the question is going to be to find the integral, or the antiderivative rather, on a particular interval.
Okay.
Of course, what we'd expect with definite integration. And it would be the under root of 2x plus 1 dx.
Okay.
And let me go ahead and let's see here. Right, so that's about it as far as this question is concerned.
Okay. So what have you tried so far?
Well, so if this question were strictly something like this, for instance, 2x plus 1 dx, without it being sort of bounded on a particular interval, I would solve that via use substitution.
Okay.
And I think that's about as far as I reach with these types of questions. I'm just not too sure how to sort of put this in the context of definite integration.
Yeah, so there's two kind of approaches. So it sounds like you're comfortable with the indefinite integrals. There's two sort of ways we can approach a definite integral using use substitution. So one way, a way that I tend to like, is find that antiderivative in terms of x and use that for the definite integral. So let me kind of write a couple notes here. So let's say we find the antiderivative. Forgive the handwriting there, but
sure.
So, sorry, go ahead.
No, I was just saying sure. I mean, your handwriting's fine.
Yeah. Yeah. So let's say you do what you'd normally do with the indefinite integral. You find that antiderivative in terms of x. Then you can solve the definite integral as we normally would.
Right.
Using that antiderivative.
Sure.
The other approach would be using u substitution, but at the end leaving it in terms of u, and you instead transform the bounds of your integral and solve the integral that way. Right.
Okay, so I suppose our strategy here moving forward would just be to treat it as an indefinite integral, and then use the fundamental theorem of calculus to, or in other words, plug in the upper and lower bounds into f of x, capital F of x.
Exactly, yeah.
Okay, so I did try doing that, and so let me just go ahead and breeze through it real quick so we can get to that part at least. So if we were to, so I guess we'll take u as being 2x plus 1.
Okay.
And
seems like a good choice.
du would be the derivative of 2x plus 1 multiplied by dx. So du would essentially just be 2 dx, and then dx in terms of du would just be du over 2.
Right.
And then I guess we can then have we could transform our integral into being into let's say u 1/2, and we would have du over 2, which I guess we can write this as being 1/2, and then from 0 to 4, 1/2 du, and then take the integral. Is that would you take the integral from this point, or what would sort of be your approach here?
Yeah, so from here, I would find that antiderivative and replace things with x. A quick note, this is like a kind of a technicality thing, but this ties into what I was talking about with two different approaches. Since we changed our variable from x to u, we want to be careful about what we write for the bounds of our integral, because they're different now.
What exactly do you mean by different? I think they're on the same interval, right? 0 to 4.
It's right. It's the same interval from x equals 0 to x equals 4.
So I suppose we can just assume that this is now on the interval from u equals 0 to u equals 4. I mean, I suppose that would be the same. We're just changing the name of the variable, correct?
Yeah, so we're changing the name of the variable, but if later on we go back from u to x, then we can use the same bounds of integration, no problem. But I want to draw your attention up where we define u as 2x plus 1.
Right.
So that means if x is equal to 0, that's like saying that u is 1. And if x is 4, the equivalent value for u is going to be 9.
Are you solving for
yeah,
for u here?
Yeah, let me write it out so it flows a bit better. So the integral of this function from 0 to 4, from x equals 0 to x equals 4 is going to be the same thing as the integral from u equals 1 to u equals 9.
And is there any, like I understand that you're plugging in x equals 0 and x equals 4, the lower and upper bounds into what we had for u, but I'm curious as to know, and this is of course just an algebraic manipulation, but I'm curious as to know why we choose to do that. In my opinion, u or x, these are just two different variables, and they're on the same bound, 0 to 4, right?
Yeah, so you're right in that they're two different variables, but they're not necessarily on the same bounds, because when we this is actually, I think this will help. When we're writing bounds of integration, they are specifically chosen to match up for the values of the variable we're integrating over.
Right.
So if we have an integral, stuff dx, that means those bounds specifically relate to x. When we say something like, let's say that u is this variable that's equivalent to 2x plus 1, or in other words, for a given value of x, the equivalent value of u will be twice it and then add 1. So when we change our variable of integration to u, we need to use that same transformation on the bounds of integration. So basically, when we do something like u equals 2x plus 1, we are changing everything we're working with. And we're doing it in a way that once we're done, we can switch back, no problem. But while we are working with this different variable, the values themselves are going to be, we have to think of these values in terms of what they would be as u, not necessarily as x.
Right.
So if we have u go from 0 to 4, that's different than if x was going from 0 to 4.
But surely, I understand what you're saying to an extent, but surely geometrically, if we had, if we were finding like the function 2x plus 1, I would assume it would look something like this. So if the interval was, as we're saying, from 0 to 4, then we would have this particular area here,
right,
that we need to find. And I think what you're saying is that had this been in terms of u, we would have had a different curve.
Right. If we had the y-axis scaled identically, the curve would have looked different, but the values on the horizontal axis would be different as well.
So you're saying that this is the curve for u, hypothetically, from, so it's the curve for 2x plus 1. But you're saying that when we change this particular function here from u to u raised to the 1 over 2, that's not the same thing as this curve.
Right. For the sake of an easier picture, going with this, just plotting the 2x plus 1, forgetting about the square root for now, because it's the same principle. Right, so we have, if we have an xy chart, right, then, right, 2x plus 1 would look a little exaggerated, but something like this.
Sure.
Whereas the line u would be less curved and it would pass through 0.
Okay.
And what we're saying when we're doing this with integrals is x from 1 to 4, this area is going to be the same. Or sorry, that should be a 0 to 4.
From 1 to 9.
Right.
On the different curve, essentially.
Right. It's like it's a shallower curve, so it's not going to get as tall. So an equivalent area would have to span a larger horizontal if we were looking at this geometrically.
Sure, absolutely. That makes a lot of sense. I think the graphical relevance sort of ties it all in together.
Yeah, and I mean, we're finding areas under curves, so it makes perfect sense to go to graphs. Yeah.
Sure. And I did have one more question for you. And this is again another conceptual question. Over here, hopefully you see what I'm underlining.
Let's see. The blue box around our substitution.
Right.
Yeah.
So so really what we did was we had u, and we identified u as being 2x plus 1, and then we took the derivative of u, and we also took the derivative of 2x plus 1. So in other words, we took the derivative of both sides. And then what happened later on was we actually multiplied by dx on both sides. And I'm curious as to know why that's even possible, because it seems as though d over dx is just notation for finding the derivative, just as this particular sign here, this elongated s, is notation for finding the antiderivative. But in the same way we don't perform algebra with the antiderivative symbol, I find it questionable as to why we can perform algebra with the derivative symbol.
Yeah, and so there's kind of a step happening in between, which makes this possible. And you're right, it's a very unfortunate notational kind of issue. Later on, you'll probably learn about something called differentials, which kind of play with dx's and dy's. I'm gonna redraw that kind of stuff a little bit off to the side real quick. So, right, if we start with u equals 2x plus 1, and we take the derivative of both sides with respect to x, let's say, then the left side, technically, it's the derivative of u with respect to x, which we would write du dx.
Right.
Equals 2. And then we multiply that dx over to get du by itself. And that multiplication is because once, so like d dx is an operator. We can't just multiply x around and be left with this d. But once we get to this du dx, it represents, it represents a ratio of change. It's a change of u with respect to the change of x, where du dx in that case is like a delta u over delta x.
Sure.
And so at that point, we're not dealing with an operator anymore. This is a value du with respect to dx, and we can multiply that dx around. Because at that point, it's not part of the operator. It's part of a ratio of change in u to change in x.
So you're actually performing algebra with your change in x, which is a concrete number, which you can perform algebra with.
Right. It's like a part concrete number and part conceptual number, but it's such a quantity that we can do these sort of algebraic things with it.
Okay. Okay, awesome. So I guess we can just move forward with the question here. I feel like we went on somewhat of a tangent.
I think that is a very important and worthwhile tangent, though.
Yeah, the tangent thing was really just a pun because, we're dealing with
yeah.
But okay, so I suppose now sort of finding where we were before, we were, so it seems as though we had this, we had from 0 to 4, and then we took out the constant here, and then we had u 1/2 du, and it seems as though we were about to take the integral here, so that'd just be 1/2, and then u 3 over 2. Let's see, 3 over 2, and we would multiply by the reciprocal, 2 over 3 du, or actually we wouldn't use the du here, would we?
Right.
And then we'd have, seems like we'd have 1 over 3 u 3 halves, and then I guess we just have 1 over 3 then. So we would just plug in u at this point, I suppose.
Right.
So,
plugging in the u values.
Right.
If not necessarily the x values, though.
Sure. So 1 over 3, and then we would have u here as being 2x plus 1. And so I suppose now we can evaluate for, I think we discussed that the evaluation would thus be from, I believe it was from 1 to 9.
So the evaluation from 1 to 9 is only if you leave it in terms of u. Because you've brought it back to x being the variable, your bounds will be 0 and 4 again.
Interesting. So let me go ahead and, so you're saying there's really two ways to go about this, in that we can leave it in terms of x, which the bounds will be the same, or in terms of u, in which case we would have to have the bounds correlate with the transformed curve. Okay, so just because I think I know how to deal with if it were in terms of x, let me just go ahead and have it in terms of u. So we would have u here, 3 halves. So from this point, I would just plug in, let's see here. So I'd plug in 0, 1, and 9 into this particular guy here.
Right.
So it would be 1 over 3, 1 over 3, 9, 3 halves, minus 1 over 3, 0, 1, 3 halves.
Mm-hmm.
Which I guess is just 9, 3 halves minus. Could that be sort of a final?
So unfortunately, with exponents, we can't combine, when the base is different, we can't combine over addition or subtraction.
So, okay. So I think that's, okay, so then this would just be it then?
Yeah, that's, yeah, we could get it down to just a number, but I think that would be fine. So what I'd like to do is show you that if we'd have done it with x's, we'd get the same answer.
Right.
Right, so if we replaced u with 2x plus 1, and we evaluate from 0 to 4, then we get that 1/3, plugging 4 in, plugging 0 in, and as you can see, we get the exact same thing.
And how exactly, I think you mentioned before that we could get it in terms of the number. So how exactly would you go about doing so?
Yeah, so I would do, so 9 to the 3 halves, I'm going to write that as the square root of 9
Sure.
to the 3rd. And then 1 to any power is just 1. Okay. So this is going to be 1/3 of 3 cubed minus 1. So that's going to be 1/3 of 27 minus 1, or 26 over 3.
Right. Sure. Okay, so it seems as though I just have to keep track of my u's and x's in terms of what I'm doing. But I think it makes sense geometrically and of course algebraically. So with definite integration, I have to make sure that my bounds are consistent, and that should reflect algebraically as well.
Yeah, as long as your bounds match your variable, you're fine.
Okay, that sounds good. All right. Well, I think I got everything that I felt like I needed from this.
Great.
And thank you for giving the time.
Hey, it's fun stuff.
Yeah, it's fascinating. Really is.
Yeah.
So if I have any more doubts, I'll surely log back on.
All right, sounds good.
All right, have a good one.
You too.
Bye.
Bye.